So what do we have right here? Well, this is just a water molecule. And this right over here, let's see, we have 1, 2, 3 carbons in our backbone. So this would be methethpropane. We all have single bonds right here. So this is propane. Let me write that out. This is, give myself some space, propane. And then on the number 2 carbon, I have both a methyl group and a bromo group. And bromo comes before methyl in alphabetical order, so I could write this as 2-bromo, 2-bromo, 2-methyl, 2-methyl, methyl propane. So that's this molecule that we have right over here. Now what we're going to imagine, it's sitting in some water, and I have one water molecule drawn right over here. Let's imagine that we have this bromine right over here. It's pretty neutral, and it's neutral because it has, or it is neutral because it has 7 valence electrons. 1, 2, or you could say, it has the charge equivalent. It has 1, 2, 3, 4, 5, 6, and then it has half of this bond that's composed of 2 electrons. So that's what's keeping this neutral right over here. But we do know that bromine, well, you know, it's not completely unstable if it were to take an electron, because that would get it to 8 valence electrons. We know that it's more electronegative than carbon, which means that if it's sharing a bond, it's more likely to take the entire bond than carbon is. So let's imagine a scenario. Let's imagine a scenario where bromine takes these 2 carbons in this bond right over here. And this isn't going to be a super fast thing that happens because this molecule right over here, the 2-bromo, 2-methyl propane, is actually reasonably stable. So I'm not saying that this is going to just happen automatically. It's going to happen super fast, but it could happen. And so to show that this isn't going to be only a one-way reaction, I'll show that it's in equilibrium. So the equilibrium, I'll draw 2 arrows like that. And so once this happens, the bromine would turn into a bromide anion. So let me draw it right over here. So the bromide anion, so it's going to have 1, 2, 3, 4, 5, 6, and then both electrons from that shared bond. Both electrons from that shared bond, it now has a -1 charge. Now, if that happened, what would happen to this leftover, to I guess what's now going to be the thing that the bromine was connected to, I guess you could say. Well, let's draw that. So we have this carbon, our number 2 carbon. We have CH3 right over there. Then we go back to a CH3, and then I had this blue methyl group. So I had this blue methyl group right here, and the way I'm drawing it, it kind of pops out of the page. My best attempt to draw it popping out of the page. So this is it popping out of the page. And now what's its charge going to be? Well, it just gave up half of this bond, the equivalent of an electron's charge. So it just gave up, you could kind of think of it as giving up an electron. So this is going to have a positive charge. This is going to have a positive charge. And a positive charged carbon like this, we would call this a carbocation. So this right over here is a carbocation, positive charge. And the reason why this is not a crazy thing to happen is that this is a tertiary carbon, which means it is connected to 3 other carbons. 1, 2, 3. A tertiary carbon, one way to think about it is that this positive charge can kind of be shared with its brothers a little bit more. So a tertiary carbocation is more stable than a secondary, and definitely more stable than a primary. Secondary would be if it was only connected to 2 carbons, but this is tertiary. So let me write this down. This is a tertiary carbocation. This carbon is connected to 3 other carbons. That's where the tertiary comes from. So once again, it can happen. I'm not saying that this reaction is just going to go super fast in that direction. That's why we did these equilibriums. These equilibrium arrows. Now let's bring this oxygen into play. So let's bring not the oxygen. Let's bring this water into play. So this water, as you can imagine, the water is neutral. It seems pretty reasonable in this state, but it does have the oxygen end of the water does have a partial negative charge. We've seen in the past. We've seen in the past that because oxygen is a lot more electronegative than the hydrogens, that you have a partial negative side on the side of the oxygens, and you have a partial positive charge on the side of the hydrogens on the side of the hydrogens. And so you have this positive carbocation. This has a partially negative charge. So you could imagine that this molecule might be attracted to this nucleus. Now, it's not going to be super attracted the way that a hydroxide anion would. A hydroxide anion has a full negative charge. This only just has a little partial negative charge, but it could still be attracted to something very positive like this. So in this situation, the water molecule is a weak nucleophile. So this is a weak nucleophile. No, not as strong as a hydroxide anion that has a full negative charge, but if it sees something positive like this and it bumps in the right way, you could imagine that one of these pairs of this oxygen would then go, one of these pairs on this oxygen would then go and essentially form a bond with this carbon, making this carbon right over here neutral. So what is that going to look like? And this might happen this would happen faster, so I'm not going to do this as an equilibrium. This could happen like this. And let me just copy and paste the bromine so I don't have to redraw the whole thing. So let me copy and let me paste it. So that's our bromine right over there. Draw it right there. Actually, let me erase this little smudge and make sure it still has a negative charge. So negative charge, it's a bromide anion now, and now let me draw everything else. So I have this carbon, let me scroll down a little bit so I have some space. Carbon, I have the carbon in the back, CH3, I have the carbon on top, CH3, I have the carbon in front, like that, CH3. And now my oxygen, or I should say this molecule right over here, the water molecule, has attached to the carbon. So these two electrons, you could say they've attacked the carbon. They now form a bond with the carbon. They form now, so these are those two electrons in this covalent bond. And now let's draw the rest of this. So you have the oxygen, you have these two electrons right over here, these two valence electrons. And then you have one hydrogen and then another hydrogen. Now, what is going to be the charge? What is going to be the charge right over here on the oxygen? Well, it had a partial negative charge just because it's more electronegative, but it just gave essentially half of a bond, half of a pair. It's now sharing a pair with this carbon. So it's equivalent of giving up one electron's equivalent of charge. So you would now say that this thing right now has a positive charge. So you could imagine maybe another water molecule comes along. Let me draw another water molecule right over here. We're sitting in water, so there's plenty of water molecules. So another water molecule might come along and say, okay, well, this thing right over here is positive, but the oxygen is hogging these bonds a little bit more than the hydrogens, especially now that it's become positive. And so this might give its pair to a hydrogen proton, and then this hydrogen, and then this bond with the hydrogen will go entirely to the oxygen. Let me draw that in a different color. So this bond right over here goes entirely to the oxygen. Electronegativity means if this is more electronegative than that if a bond breaks, that pair is more likely to go to the more electronegative molecule. Or I should say the more electronegative atom. So what will this look like when all is said and done? So let's draw an arrow like this. So let me draw my main molecule. So I have the carbon. It has bonded to another carbon right up there. It's bonded to another carbon right over there. We have our carbon in front. Just like that. We have the bond with our oxygen. So we have our bond with our oxygen right over there. So that's our oxygen. We have this bond with a hydrogen. We have this pair. And now it has gained this pair. That was with that hydrogen. So just like this. This is now neutral. It went from being positive. Over here, it only had half of this bond. So it's kind of the equivalent of one electron charge. Now it has the whole bond. So now it has the equivalent. It literally has both electrons. So now this thing is neutral. And now this molecule right over here becomes a hydronium cation. Let me draw that. So this water, so let me see. So that's the two hydrogens right over there. This is that pair that is on top. And now it is sharing this pair with the hydrogen, essentially with a proton. So with the hydrogen, with this hydrogen right over here, with this hydrogen right over here, and now this will have a positive charge. This is a hydronium cation, and maybe this bumps into another water molecule and does the same thing with it, and it just keeps going on and on and on. And of course, we can't forget our bromide anion friend. So there's our bromide anion friend. Got a negative charge right over there. And so what are we left with? Well, we are left with, well, there's a little bit of, there's this hydronium cation has a positive charge. You have this bromide anion. And now what is this molecule now called? Well, we'll go into more detail in the future, but when you have a hydroxyl group attached to the carbon backbone, it is an alcohol. And so our main backbone, once again, has 1, 2, 3 carbons, so that tells us prop, but instead of just saying propane, it's propanol. So let's write that down. This is propan. And some people say just propanol generally, but if we want to be a little bit particular, this is the hydroxyl group is attached to the number 2 carbon. So we would say propan 2 all. And of course, we still have this blue methyl group. So we could say 2-methyl, let me make this 2-methyl propan 2 all is what we are left with. Now, let's think about what we can name this reaction we just saw. Well, we've just substituted a bromo group with a hydroxyl group. So I think it's reasonable to say that this is going to be a substitution reaction. Substitution. And we substituted with it was a weak nucleophile, but it was a nucleophile nonetheless. So it involved a nucleophile. But this one, unlike the Sn2 reaction, in the rate determining step, and this is the rate determining step, this is the slowest step of the process. Everything else will just kind of start happening once this thing happens. This thing kind of is in equilibrium. This is the rate determining step. Only one reactant is involved in the rate determining step. One reactant in rate determining step. Rate determining step. In this case, it was the bromo group. So you might guess what we're going to call it. It's substitution involving a nucleophile. So nucleophilic substitution. You can imagine it stands for nucleophilic. And only one reactant is involved in the rate determining step. So this right over here, this whole reaction that we've now drawn, is an Sn1 reaction. We're now going to explore one of the most fundamental reactions in organic chemistry. And first, let's look at what are the things that are going to react. So over here, I have a hydroxide anion. It has a -1 charge, and that -1 charge comes from the fact that oxygen is neutral if it has 6 valence electrons, but this has 1, 2, 3, 4, 5, 6, plus half of this bond with hydrogen. So you could think of that as another electron, or it's got half of these two, so that's another electron, which gives it a -1 charge. Now this right over here, it has 1 carbon, I guess if you could say, in its backbone. So you would use, it's a methane, and it has a group right over here consisting of bromine. So this is bromomethane. So let's think a little bit about what might happen under the right conditions. So this hydroxide anion, we've already gone over the fact that you can kind of view it as having an extra electron, which gives it its negative charge. Well, if you have a negative charged anion like this, it will be attracted to positive things. And one example of a positive thing is a nucleus. And so in this reaction, we are going to refer to this hydroxide anion as the nucleophile. Nucleophile. Phile literally refers to things that something likes, this thing likes. It's a nucleus lover, I guess you could say. And so it might want to share maybe a pair of electrons with a nucleus. Now over here, I have this bromo group in the bromomethane, and bromine is quite electronegative. It is more electronegative than carbon. So even in this bond, we have 2 electrons in this bond right over here. Bromine is going to hog the electrons a little bit more than carbon. And also electronegativity says that if this bond were to break, it's more likely that this pair, the pair that's in this bond, is going to go to the bromine than it's going to go to the carbon. So the way that this reaction works, and it's really kind of happening in one step, and this is key to the name of this reaction, as we'll see in a second, is that this nucleophile right over here might say, hey, let me share, I got this extra charge, let me share some of that charge with a nucleus, in this case the carbon. Let me draw it like this. In this case, the carbon. So it would share this pair, which would form a bond. Carbon would have half of the pair, oxygen would have half of the pair. So it would share this pair. It would share this pair with carbon. Now, if carbon is now sharing half of this, it's essentially kind of getting half an it's getting an electron. It doesn't need this electron, which bromine is already hogging a little bit. And so bromine would take this entire pair back. Whenever we draw full arrows like this, just normal arrows that you're used to seeing, it's referring to the action of pairs. So this whole pair is going to bromine. This pair right over here is now going to be shared with the carbon. It's going to form a bond with the carbon. So when we do both of these steps, after both of these steps, it would look like this. It would look like this. Let me draw my bromine first, which is now going to become a bromide anion. So bromine, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And now it gets both of these electrons from this bond. So it has both of those electrons right over there. Now, this will have a -1 charge. How do we know that? Well, bromine is neutral when it has 7 valence electrons. This thing now has 8. So this now has a negative charge. Now let's think about what happens to all of this business. So let me draw up my carbon first. My carbon. Now let me draw this hydrogen that's popping out. So this hydrogen that's popping out, let me draw it like that. So that's the bond, trying to show that it's popping out of the page. So that's that hydrogen. I just made them different colors so we can keep track of the different hydrogens. Then the hydrogen that's going into the page, that's that one right over there. Then you have this hydrogen that's going up. So that hydrogen right over there. And now the hydroxide anion has bonded to this carbon. Now it'll be a hydroxyl group. So this thing has now bonded. So let me draw the bond in the color of these 2 electrons. It has now bonded. So those 2 electrons now make up this blur, this bond right over here. And now we have our oxygen, but with these 2 right over here, these 2 right over here, and then the bond to the hydrogen. Now what just happened here? The oxygen is now neutral. Why is it neutral? Well, it has 1, 2, 3, 4, and then it has half of this bond, so you could view that as an electron or the equivalent of an electron charge, and then it has half of this bond. So it has the electron charge equivalent of 6 valence electrons, which makes oxygen neutral, and now bromine is negative. So one way to think about it is that the negative charge has been transferred to the bromine in this reaction. Now, in this reaction, bromine has left, and that's why we call this the leaving group. We call this right over here the leaving group. The leaving group. The leaving group of the reaction. This thing right over here is the thing that is going to leave. That is the leaving group. Now, the other thing that you might find interesting, it looks like kind of this hydroxide anion, some people would even say attacked this bromomethane. The bromomethane left. The hydroxide anion, the bromine left, not the bromomethane left. Attacked the bromomethane, the bromine left. So in some ways you would say that there's really 2 reactants over here. You have the hydroxide anion and you have the bromide anion, and this carbon right over here with the hydrogens, this was kind of the thing that just to some degree facilitated the reaction, that this thing bumped into it and attached, and then this thing left. And so in this context, we would call the carbon with the 3 hydrogens, we would call this the substrate. The substrate. Now, what should we call this reaction? Well, one way to think about it is we substituted this bromo group with a hydroxyl group. So it might make sense to call this a substitution reaction. Substitution has occurred. Substitution has occurred. Now, what did we substitute with? Well, we substituted with a nucleophile. We substituted with a nucleophile. And how many reactants were involved in the rate determining step? And I know that might not make a lot of sense to you, but this had essentially one determining step. This had to want to bump in the right way, and this would want to have to leave right at the same time in order for this, or roughly the same time, in order for this reaction to occur. So this reactant and this reactant were involved in figuring out, well, how fast is this reaction going to happen? And we're going to see future reactions where you don't have both reactants involved in the rate determining step. We'll see only one reactant involved in the rate determining step. But I'll just write this right over here. Two reactants in rate determining step. There's a garbage truck outside. I think the garbage truck has left now. Safe to resume. So as we were saying, there are two reactants involved in the rate determining step. And so the shorthand for this reaction is to call it an SN2 reaction. An Sn2 reaction. It's substitution with a nucleophile where both reactants are involved in the rate determining step.